Hi, this is Dr. Liu. In this video, I will discuss Kepler's laws of planetary motion. So, what Kepler discovered after decades of his own observations and looking into his predecessors' results were very stunning. So, the first law he discovered was how the planets were moving. They were actually moving in elliptical orbits, although some of these ellipses look more like circles, such as us, our Earth around the Sun. So the first law is a planet follows an elliptical orbit. Let's say path. And with the Sun at one of the two foci, so focus. So this is what the orbit would look like, something that looks like this, a bit more elliptical. So here's a focus, so here's the Sun, and here's the planet. So the planet will just go around the Sun like this, and that's his first observation about how a planet orbits the Sun. So number two, this one starts to get a bit strange, and so the planet motion, you can imagine there's an imaginary line between a planet and the Sun. So here's an imaginary line. So I would just say imaginary line with equal distance, equal area. Equal in time. So what this means is, as the planet moving along its orbit, this imaginary line is going to change location, and we can imagine that between these two positions of the planet, this line is sweeping forward, so it has swept an area. Let's color this with blue. So it has swept an area just like that, and Kepler claimed that this area swept is going to be equal with equal time spent. So what does that mean? Well, if the planet were further away, say the planet was here, so this, sometimes we call it broom, has a longer handle. So in order to sweep the same area, the planet doesn't have to move as much arc distance as it had to do when it's closer to the Sun, because the broom has a longer handle. So I would just draw some arrows with less lengths. So this area is already large enough to compare with this exactly. So the planet doesn't have to move that fast. But as the planet gets closer and closer, the broom handle gets so short, if this elliptical orbit is very elliptical. So it has to cover more distance here in order to sweep the same area with the same amount of time. So the planet simply moves faster as it comes closer to the Sun, and it moves slower as it moves away from the Sun. So if I just imagine these areas all the same, this is a thinner but longer size, this is a wider but a shorter size, and let's imagine these are all equal areas, we can conclude that as the planet is further away, this is slow. As the planet gets closer and closer to the Sun, it's fast. Okay, so and then it slows down again as it is departing from the Sun while it's going to come back, right? So this thing is just very strange. After the first encounter I thought this is really strange. But later I started to understand there's a conceptual understanding of this is well you're as you're approaching the sun you're being pulled toward the sun, right? So the gravitational pull accelerates you, so you're moving faster. But as you're going away from the sun, the gravitational pull is pulling you back toward the sun, so it slows you down and it makes you move slower. But what exactly is causing the area being the same is still not explained, right? And I don't really intend to explain it here and for you to entirely understand this, but there is a quantity here, a conserved quantity, which is called angular momentum. And the quantity is always the same regardless where the planet is on its path. So this quantity being the same maintains the area. So that's the source of this exactness, the area. But on the conceptual level, you know the planet is actually falling toward the sun. It accelerates, it gets faster, and then it kind of moves away from the sun. Just like you toss some object up from the ground, it slows down. And so it slows down, speeds up, it's kind of falling toward the sun and then falling away from the sun. So that's what causes conceptually slowing down, speeding up of planets. All right, so let's move on to the third law. The third law is very interesting. It's numerical. So it mentions two quantities. So one quantity is the period. So period squared. Oops. Period squared. So that is t squared. And the second quantity it mentions is mean distance. Cubed. So if you call that a mean distance r, and you cube it, so then it mentions two separate planets, or any planets, any two planets. So period squared and mean distance cubed. So for each planet, it has its period orbiting the sun, and it has its mean distance cubed. So that's basically the semi-long axis, basically half that whole distance over here. So that's the mean distance cubed. You cube that distance. So let's say planet 1 and versus planet 2, any two planets. So the planet 1's period squared over planet 2's period squared is the same as planet 1's distance to the sun cubed over planet 2's distance over the sun's cubed. So that's really hard to figure out. The squares is somehow proportional to the cubes, right? So what this tells you, conceptually speaking, is say if this planet has a larger distance to the sun than another planet, then it also has to have a longer period orbiting the sun than the other planet, which is closer by. So if you look at planetary motion, the planetary motion is not like all the planets on a plate, stuck on a plate, and the whole plate somehow just rotates around the center, meaning that all planets have the same periods orbiting the sun, but it's not. These further away planets will spend longer time orbiting the sun, and that means their solar years are longer than ours. So ours are longer than the inner we're one of the inner planets, but there's also the Mercury and Venus. They're closer, so they'll have shorter periods orbiting the sun than us. And we have a shorter period than Mars. Mars has a shorter period than Jupiter, and so on and so forth. So let's take a look at this NASA table. It has planetary facts on it. So from left to right, these are all the planets here, and we can ignore the mass and other things. We can look at the let's see, where is this? This is distance from Sun in 1 million kilometers of units, here's also orbital period in amount of days. These are Earth days. So we can see that the Earth has a period of 365 days plus a little extra. So let's do some calculations here. We'll pick two different planets. Since we have Earth, let's pick Earth here. Let's also pick Mars. So Earth and Mars, and we're looking at the distance to the Sun. So we have 149.6, and we'll just do 150. And we also have the Mars. Mars is 228. So 150 versus 228. The units are being the same, and we can divide them out, right? So 150 and 228. So let's say that R1 is 150. The unit is 10 to the 6 kilometers. And R2, 228. That's 10 to 6 kilometers. And let's do periods. So period 1, that's Earth, 365 days. And for Mars, I wish I can remember that. So, okay, for Mars, the period is 687 days. So 687 days. Okay. And the units don't really matter. I'm not using seconds, I'm not using meters, but if I make a fraction between these two exact units, so they'll just cancel themselves, right? That's the same thing. Days will cancel days if I just use days. Okay, so the fraction of period squared, t1 squared over t2 squared, is equal to 365 squared over 687 squared. Let's use our calculator again. So 365 squared over 687 squared. So we have a factor. Let's keep 3 digits after decimal. 0.282. Okay, 0.282. And then we'll calculate radius cubed over another radius cubed. So that's 150 cubed, not square, over 228 cubed. So hopefully we'll see that 282. So 150 cubed over 228 cubed. There we go, very close, right? So 0.285. So 0.285. So what's causing all these interesting relationships? You might want to know that. And plus, what's the difference between these two? Why are they slightly different? Well, there are other effects. The Earth and Mars, they're affected by the Sun, but they're also affected by other planets. So there could be some corrections to that exactness that only considers the Sun as the only source of a gravitational force. So let's derive this. We will need basically two things. It's not exact derivation, but it's kind of a demonstration. So first we assume a circular orbit. That's okay because most of these elliptical orbits are circular enough. So we assume circular orbit, and we ignore other effects of other planets. So, and then we only consider sun with planet. So let's draw a diagram now. Now we have orbit, right? So there's a distance r here, and we know that the planet is experiencing uniform circular motion with a circular orbit. So the planet would require a centripetal force in the magnitude of mv squared over r. And what is providing this force? And this force is provided wholly by universal gravitation. There's no other force binding a planet to the sun. So that's just that. So this magnitude is equal to g m. This capital M is the mass of the sun. So let's put this capital M in the middle, lowercase m next to the planet, and that is gmm over r squared. Okay, so we still are not seeing the squares and cubes yet, but that's okay. And if we look at this, we can make a calculation here. What is the orbital velocity? The orbital velocity must be the circumference over the period, right? The circumference is 2 pi times the radius, and then divide by period. So I'm going to substitute that in here. So the left side is mass, and this whole thing squared is 4 pi squared r squared over t squared. I still have this this r here in the denominator, so let's not forget that. So that's the left hand side, and the right hand side has this g m over r squared. Okay, so let's see what could be divided out. The mass could be divided out, and here's one r, and this r will be just a first power. So we have 4 pi squared over t squared, and here's only one r left, and the other side has gm over r squared. So if I multiply both sides by r squared, and this 1 over r squared will be gone, and this side will be r cubed. So let's do that. Multiply by r squared on both sides. So 4 pi squared r cubed over t squared equals gm. Okay, and if I multiply this whole equation by t squared on both sides, and this 1 over t squared is gone, so I have 4 pi squared excuse me, r cubed equals gm times t squared. And then if I divide out the gm, or multiply by 1 over gm, I get 4 pi squared over gm r cubed equals t squared. Excuse me. So I can write this in two ways. One way is t squared is equal to 4 pi squared over gm r cubed. This is the alternative way to express Kepler's third law, is to express the period and the radius together. Instead of involving two separate planets, their separate periods and their separate distances. That sounds pretty complicated. This is only one planet. The one planet's own period, that one planet's distance to the sun, and the sun's mass. And the planet's mass doesn't even matter because it's much smaller than the sun's mass. So this tells you, this is alternative law 3. This tells you how to relate period with the distance. This gives you a much better, much more clear picture. If you have a greater distance to the sun, you have a greater period, right? Okay, so let's try to make this into the original Kepler's law, third law's format. So that I'll just divide both sides by r cubed, or just multiply both sides by 1 over r cubed. So what I get is t squared over r cubed equals 4 pi squared over gm. Okay, so up to now, I didn't even specify which planet. I just have to specify that one particular planet's period and its own distance. So this is a pair that exists on one planet. The period it makes is its orbit around the sun and its distance to the sun. So this means if I have two separate planets, I can do two separate fractions. So for planet 1, I have t1 squared over r1 cubed, and that is equal to 4 pi squared over gm. And for planet 2, I have a different period, t2 squared over r2 cubed, a different distance, but that is still supposed to be equal to 4 pi squared over gm, which means this period squared over radius cubed is equal to the other planet's period squared over its radius cubed. So that's how I can prove the third law. Basically, not exactly proving, but proving it works in a circular orbit. Try to prove it with an elliptical orbit. It works. It's just more difficult to do. So now you see where this comes from. A nice application of this law is, say, if you know the distance from, say, r, a distance from the planet's center, say if you have a satellite, say we have a man-made satellite orbiting Earth, and what is the period of that satellite? So you just have to find out the distance the satellite has to the center of the Earth. So this application is it's just let's draw a little satellite. Okay, so it has a distance to the Earth, which is distance d, Earth's surface, but that has to continue to count until the center of the Earth. So this whole Earth here, radius of the Earth, so that whole thing is defined as that r, and the satellite will orbit with a period t. So this t and that r are related in this exact expression. So let's box this up. This is the alternative form of the third law. So basically, the orbit determines the period. If you're higher orbit, then you have a longer period. And if you're lower orbit, you have a shorter period. And if you're just high enough so that your period is the same as 24 hours, and you're going in the same direction as the Earth is rotating around itself, and then you would appear to be stationary up in the sky because you're orbiting the Earth as fast as the Earth is revolving around itself. So that kind of a orbit is called a Geo Stationary Orbit. So that orbit is about 86,000 kilometers from the Earth's surface, but I think you can calculate that out yourself if you know the Earth's radius and also the Earth's mass. Thanks.